Alright, we are going to do section 8.4 in this recording. So let me bring that PowerPoint up. Alright, here it is. So 8.4 is the last section for this test, and 8.4 is going to be hypothesis testing again. However, this time we're going to do hypothesis testing about a mean. Now, in hypothesis test of a mean, you're going to have to watch for a couple things. We're going to do them in part 1 and part 2 here. So in part 1, we're going to deal with the more realistic case, which is when the population standard deviation sigma is not a known value, which makes sense. Most times when you need to do a hypothesis test, you're dealing with a large population. If it's a large population, you will not know the standard deviation. If you did, well, you probably know the mean as well, and you wouldn't need to do a hypothesis test. So part 1 is more common. Sigma is not known. In part 2, we will talk about what if sigma were known, just so you can see the difference. In your homework, most of your questions deal with the part 1 case, but always check and make sure, is sigma known or is sigma not known, to know which type of problem you're dealing with. On your review sheet and on your test, you can expect to see both potentially. Alright, requirements that you need to check when you're dealing with a hypothesis test about a mean. These are different from proportion. In a mean hypothesis test, you need to check, again, for simple random sample. But instead of a binomial distribution requirement, our second condition is actually our simply normal distribution, or n greater than 30 requirement. So this is the central limit theorem. It's what gives us our normal distribution. You either need a normal population, or you need to have a large enough sample size so that the x bar distribution is normal. If you have that, then you have a normal distribution for x bars, and then you check for number 3. Is sigma known or not? If sigma is not known, you're going to use a t-test. Just like in chapter 7, you're going to deal with t. This formula is, I don't think it was in chapter 7. I believe this is new, but it's very similar to the z formula. The only change is that instead of sigma, we're going to use s, because sigma is not known. The backup for sigma would be your sample standard deviation, or s. So this is the formula you'll use as long as sigma is not known. Here's an example. Listed below are the measured radiation emissions corresponding to a sample of cell phones which comes from a normally distributed population. Very important there is it has told us that we have a normally distributed population. Okay? Now let's assume our sample is random sample. We have normal. The question is, are they going to give us sigma or not? So you have to finish reading the question. If sigma appears, or they say population standard deviation, then we're not in part 1. We're going to be in part 2. But as long as you don't see sigma or a reference to a population standard deviation, whoops, you are still in the part 1 question. You're still going to deal with a t-test. But we have to read the rest and make sure. So use a 0.05 level of significance to test the claim that cell phones have a mean radiation level that is less than 1.00, whatever that is. So here's our sample. Notice nowhere in here does it refer to a population standard deviation, so sigma is not known. Now at the bottom of the screen here, you'll see the x bar and the s. I will remind you, those can both be calculated using StatCrunch. So let me bring up StatCrunch. I already copied these numbers over. And let me remind you, so if you're in a homework question, like this one, uh-oh, where'd my picture go? Hold on, I don't know if it's recording. Alright, let me bring up, so if you're in a homework question, like this one here, and you need to get to StatCrunch, the easiest way to get to StatCrunch is going to question help and clicking StatCrunch. Now once you do that, StatCrunch will pop up. I already have it here. Here's StatCrunch. Now, you can calculate your sample mean, meaning the mean of the sample, and the standard deviation of the sample by using StatCrunch. So let me see, where is it? Summary stats. So go to Stat, Summary Stats, and we want to summarize the first column. So we click on column, select the column that your data is in. In this case, we only have one column, so we just want to summarize that one. And if you press compute, you should get everything you need. Probably too much, but alright, so here's in our sample size, here's our sample mean, and our sample standard deviation. Okay? So you can use StatCrunch to get some values. You will need StatCrunch in a minute, so I'm going to hold off. I'm going to keep this up here, but we're going to come back to it. I'm going to show you how to use it further. Oops, wrong button. There. Okay, so we have our sample, we have our sample mean, our standard deviation. We would do a hypothesis test at this point. Now, in our hypothesis test, you have to check your requirements. So our 3 requirements, I already said it. Number 1, we have a simple random sample. We're assuming that. Ooh, excuse me. Number 2, N is only 11. But that's okay, because remember, they told us that our population was normal. So number 2 is satisfied because it said it was normal. Number 3, sigma is not known. So you are going to calculate your t-score. All right. I'm going to actually bring up a place where I can write all this out. So in our question, we had a claim. What was the claim that we are testing? Let me go back to our question. So they want us to test the claim, and then here's our claim, that cell phones have a mean radiation that is less than 1, whatever that is. So cell phones have a mean radiation less than that's our claim. Now, we need to write that in symbols. So the symbols here, notice they have the word mean. That means that you need to use the symbol for mean. Now remember, when we test hypothesis, we're testing it about a whole population. We use the sample, the x bar, to make a determination about this mu value. But in the claim, they state that the mean, mu, is less than 1 WKG. So, after you write your symbols, remember, you write the opposite. All of these are going to be the same process as we had in 8.2 and 8.3, but symbols are going to change a little bit. So instead of mu less than, what's the opposite? Greater than or equal to would be the opposite. Now that you have all the symbols, you can figure out your hypotheses. So our null hypothesis is always going to be which one? The one with the equal sign. So this is the equal sign one. That one is going to go to our null. But you just write the equal sign, not the greater than, just the equals. But the other set of symbols is going fully as your alternative. So mu less than 1. Like I said in the last chapter, I like to make a note of which one of these hypotheses is my claim. And I also like to make a note of how many tails we're dealing with. Remember, tails are determined by the alternative hypothesis. So in our alternative hypothesis here, it says mu is less than 1. So if we had a mean that was far enough less than 1, we could reject the null. So less than, which direction would be our rejection? Less than should be considered to the left. So this would be a left-tailed test. Okay? Very, very important sentence. Always assume the null is true. Without that sentence, you cannot continue. Alright, now the test statistic, which I already checked the requirements. I'm just going to make one little note to help you remember. We have X was told to be normal, so we have a normal population, and we have sigma is unknown. Those two requirements are what tell you that you can do a t-test and you have to do a t-test. Sigma being unknown means you have to use t. So our formula was x bar minus mu divided by s divided by the square root of n. So our sample data, I have to go back to the other screen and get it. X bar was 0.938 minus mu. What is the mu value? Where is that? We don't know what mu is. That's what the whole purpose of this is, right? Oh wait, we made an assumption. We assumed the null hypothesis was true, and the null hypothesis says mu equals 1. So I plug in 1 for mu, and you go back and get my s, 0.423 divided by the square root of n, which was 11. So we plug all this lovely stuff in our calculator, which I need to bring up here. 0.938 minus 1 divided by 0.423 Now don't get confused, I'm multiplying, don't look at my calculator, it's a weird calculator. Alright, so my t value is negative 0.48, was that a 6 when I round? Yes, 6. T-scores we usually round to 3 decimal places, but 3 is a good rule. T is when you have to round to 2. Alright, so we have our test statistic. At this point, you have a choice. You can go one of 2 routes. Let me go back to my PowerPoint because I already have it all nicely typed out for you. So notice I have my t-score, negative 0.486. Did I forget my negative sign? No, I did remember. Okay, yeah, I did have the right thing. Alright, so our t-score is here. Now, this is a picture which would be considered your critical value method. So we've drawn the bell curve. We have marked our critical value. Notice in this problem, we have only marked one critical value because we only had one tail, the left tail. So we marked the left critical value. All of alpha goes in the one tail because that's where alpha goes. Alpha goes in the rejection region. In this problem, you only have one rejection, so all of alpha goes there. So how did they get this critical value? They took alpha, the area, and they looked up the critical value. So let me show you how to do that. Make sure everybody's good on this. Alright, so in our problem, we are dealing with, let's see, I need to write somehow. Get my highlighter over here. We are dealing with a degree of freedom of 10. Our N was 11, our sample size, we go one less. So we have 10 for our degree of freedom, and we have one tail, so we're up here, one tail, and that tail had an area of alpha, which was 0.05. So under 0.05 I go down, and then I go across from my degree of freedom, and there is our t-value, 1.812. However, t-scores are always given to you in the positive form. Remember that our problem is a left-tailed test, so we need the negative value. So if you look back over here at our picture, notice they put the negative sign on the t-score that I just showed you how to get. So you now have your t-score, your critical value. You also have your test statistic. Well, our test statistic is actually quite a bit closer to 0 than, well, it's actually right here, than the critical value. So because our test statistic fell in the middle, that is why we would fail to reject the null hypothesis. If our test statistic had fallen in the tail, then we would have rejected the null hypothesis. Okay, so that's the critical value method. I'm going to do another one of these from scratch, but this one's all typed up and nicely printed for you. This is what I have to show you in this section. This is new. Now, this is still the p-value method. However, p-value gets kind of tricky when you deal with a t-test, a t-distribution. You are going to need to use a calculator on StatCrunch. Now, I will also show you how to use a t-table, but first let me show you how to use StatCrunch. Well, actually, no, I'm going to show you the table first. That way you appreciate StatCrunch. Alright, so how do we find a p-value? Well, remember, you draw your little picture if you want to, like I do. You put your test statistic. So our test statistic was negative 0.486. So we want all the area to the left of that. Now, to find that area, I need to go to my t-table. Remember, this is a t-value, not a z. So let's go to our t-table. Okay, here's our t-table. And let's look up our t-value. So, remember, you have to first start by looking up your degree of freedom. I need my writing utensil again. There. Alright, so our degree of freedom is still 10. So that means we are in this row right here. Where does our test statistic lie? Now remember, these are all positive numbers, so we're going to use the positive form of our test statistic. 0.486. Where does that fall in here? Well, notice how the numbers get smaller and smaller and smaller as you go to the right? Well, yours is even smaller, so yours is even further to the right. Ooh, well, it's not there. What do you do if it's not there? Well, we're going to get a range of possible areas. Okay? No, look, go back to the top. Remember, we're doing one tail. Well, ours fell somewhere beyond this list of areas. Well, look at the areas as you go to the right. As you go to the right, these list of areas get bigger and bigger and bigger. So our area is even bigger than the biggest one listed here. So our area in our tail is at least, if it's actually bigger than, it's bigger than 0.1. Okay? That was a lot of information, so if you need to rewind and watch that again, do so. But you have to find your degree of freedom in that line, figure out where your test statistic falls. Then go up. Are you doing one tail or two tails? And figure out what interval you're in. If your interval had been in, if your test statistic had been between two numbers, you would just write that your area is between those two numbers. Ours was beyond any of the numbers, and it caused the area to be even bigger. So that's our area, 0.1, at least, greater than 0.1. Now, let me see. Oops, here, this, there. So, from the table, we can get that the area in the tail, what's shaded in the picture here, is greater than 0.1. Now, based on our alpha is 0.05. If our area is bigger than 0.1, can you compare that to alpha? Well, 0.1 itself is bigger than alpha, and our area is even bigger, so you can draw a conclusion using the table. So on your test, you will have to use the table. But they want you in this course to learn how to use some technology, so this is one area where I ask you to use technology in my stat lab. My stat lab will ask you for the exact value. So you're going to need to bring up this calculator that you see here in this picture, and I'll show you how to do that. You're just going to have to plug in your degree of freedom, your inequality, and your test statistic, and it gives you the area in the tail. Let me show you. StatCrunch. Alright. Let me make sure I got this right. Alright, so yes, you go to Stat, go to Calculators, and then we need, pretty sure it was T. Yes, there it is. Alright, so what you do, you put in your degree of freedom. Just happens to already be the correct one. Remember, N was 11, 1 less is your degree of freedom. Our X value was negative 0.486. The calculator lets you do negatives, so that's nice. And we want the left tail, so we want less than that. If we press compute, we get the area in the tail. Notice this is bigger than 0.1, but it's actually a lot bigger than 0.1. It's 0.318. That's quite a bit bigger than 0.1 in terms of the picture you see here. Remember, the whole bell curve is 1, so 0.3 is a lot of the bell curve. Now, that's how you find your area in your tail. Now, if you wanted the other end, you would simply put the greater than symbol if you want the right tail. But usually for right tails, you do positive test statistics. So if you did the right tail with the positive, you'd get the same value because of symmetry. But this calculator is how you get the number on your homework. So make sure you remember these concepts when you get to your homework. Alright, let me go back to here. But anyway, you get the same conclusion with their area that they had, 0.318. It is also bigger than alpha, so you still fail to reject the null hypothesis. If your area or your p-value is bigger than alpha, you fail to reject the null hypothesis. Oh, one more thing. Remember, the p-value in this case, because it's only one tail, is the area in the tail. In the last two examples I did in the previous section, the area, you had to double it to get your p-value. Well, that's because it had two tails. This is only one tail, so your p-value is your area. Let's just practice finding some p-values. So, assuming that software is not available, you cannot use StatCrunch. For example, your test. Use table A3 to find a range of values for the p-value corresponding to the given results. So, first of all, you're going to need your degree of freedom. So, our degree of freedom is n minus 1 or 11. So, all of these have a degree of freedom of 11. So let me go to our lovely table and highlight that row. Alright. A little bit bigger. There. Alright. So we're going to highlight the row. Degree of freedom is 11. Yeah, that was right. Okay. So this is our row. Now, our first value is t equals negative 2.007. So I need to determine where does that t value fall in this interval. First of all, you use the positive value. So where does 2.007 fall in here? It falls in between these two t-values. Now, how many tails did they tell us to do? A left-tailed hypothesis test. So only one tail. So we go up to the one tail interval at the top. So we are in between these two. So for part A, the first example, our area is less than the smaller or the big number 0.05, but bigger than 0.025. Okay? Sorry, it's bothering me. I gotta fix it. 0.025. There. Alright, now for part B, let's go find part B. And yes, my writing's gonna carry over. For part B, we have a right-tailed test, and our test statistic is 1.222. So let me get a different color here. 1.22. We're still in the same row because it's the same degree of freedom. But 1.222 is actually smaller than all of these. We're still in a one-tailed test, so our area is actually going to be bigger than this biggest area here. Okay? One more. C. Two-tailed test this time. Oh, I forgot. Let me mark that. Okay. So, in the first case here, this area is our p-value as well, because it was a one tail. In the second case, we had a one tail again, so this is also our p-value. Now, in the third case, we're going to find our area, but that's not going to be our p-value. So, in part C, so the p-value is equal to 2 times our area in one tail. Now, this is where you can use the two-tail line, though, and then you don't have to double it. So, let me go get my t-value. 3.456. 3.456 is actually over here. It's bigger than all of these t-values, which means if we go to the two-tail line, it is over in this section of those areas. So if we use the two-tail line, we do not have to double our area. If we use the one-tail line, we have to double it. So our p-value, it turns out, is less than 0.01. How do I know it's less than? Well, look at the pattern here. All of these values get smaller and smaller and smaller, and we're even further to the left, so we're even smaller than that. So ours has to be less than the smallest value there. All right. Let me clear all this out of here. All right, here we go. So that's how you do those. All right. Now part 2, and then we're going to go do an example from scratch, where you have to determine if it's a part 1 or part 2 type of problem. So when sigma is known, we use a test that involves the standard normal distribution, the z-score. In reality, like I said, this is a very rare situation. You usually do not know sigma because it's a population standard deviation. Now the procedure is essentially the same as a t-test with the following exception. You need to use a z-score formula. Now this z-score formula you have seen before. It's the same thing as before. After you plug this in and you put the z's instead of t's, everything else is the same except the p-value is a lot easier to find if you have a z-value. P is easier to find if you're working with z. You can use the table much easier for a z-score table. But you can still use a calculator or the technology on StatCrunch, but I encourage you to use the table. Alright, if we repeat the problem we just did, this would be the only real change. Instead of t test statistic, you would use the z-score. So the example refers to a left-tailed test. So the p-value is the area to the left of the z-score. So let's go make sure you understand how to find a p-value if you're dealing with a z-score. Alright, so negative 0.43. It's a negative z-score. Zoom out. Negative 0.40123. So this would be our z-score area right here. So we take our z-score, we get the area. This is the area in the tail. So we go down left. Oops, sorry. I don't have my picture up. I don't know if it's recording the screen. Just a second. Come on. Oops, what did I just do? Back. There. So, as I said, you go down the left to find your negative 0.4, and you go across until you're under the 3, and that would be the area in the left tail. So, in our problem here, notice we've written down the area in the left tail. That is the p-value because this was a one-tailed test. So, the left tail is this area, and that is your p-value. That is still bigger than alpha, so we still get the same conclusion, but you need to make sure you use z and t appropriately, because notice it is a different test statistic when you do z versus when you did t. T was a bigger value. Alright. Last step, we have one more example for you. Remember, there are examples in your test review and also in the final exam review, so use those. If you have questions, email me and I'm happy to help you, but practice writing them out like I illustrate in my examples. I'm going to write this one out fully for you right now. Alright, there it is. Let me get this out of the way. So, we have our final hypothesis test together. First step in a hypothesis is always to write your claim. So let's read the question and find our claim. People have died in boat accidents because an obsolete estimate of the mean weight of men was used. Using the weights of a simple random sample of men, we obtain these sample statistics. N equals 40, and x bar equals that value into s. Got them all. These are all sample data values. Notice we have s. What does that mean? Well, unless we see it somewhere else, that means sigma is unknown. Okay? Now, remember, you also need, in this chapter, hypothesis test of means, you also need a large enough sample to have normal. In this case, n was 40. That's bigger than 30. These are your two requirements I require you to check. Simple random sample, they do tell us in this case, but it's not always told to you, and I admit that. But you have to check for at least a big enough sample or normal distribution, and you have to check, is sigma known or unknown? Let me finish reading the question. Use these results to test the claim. Oh, here's the claim. That men have a mean weight greater than 166.3 pounds. Okay, remember, I want the words when you write your claim. Then you can write your symbols. Alright, the symbols here. Remember, we're dealing with mean, so this is mu. I see this mistake a lot. Make sure you use mu when you're dealing with mean. P, only if you're dealing with a proportion or a percentage. Alright, the mean weight is greater than 166.3 pounds. What's the opposite of that statement? Less than or equal to. What's your next step? Write your hypotheses. Your null hypothesis and your alternative. How do you determine these? Null hypothesis always is the one involving the equal sign, and you just put the equal sign. The alternative is the other set of symbols. So in this case, that would be the mu greater than 166.3. Let's make a couple notes. Which of these is our claim? The null or the alternative? Remember, the original set of symbols was the claim, so that means your alternative is our claim. Also, how many tails do we have? Greater than is which direction? Think greater, think the bigger end of the bell curve, the larger values, not the actual size bigger. So this is actually a right-tailed test. Okay? Very, very, very important sentence. You must assume the null is true. You should see by now I follow the same pattern on every single question. I would like you to follow the same pattern. That way it's easy for me to follow, and it's also an organization issue. If you rearrange anything in this pattern that I have, well, you're missing stuff. If I assume early the null is true, then I haven't written down what the null was yet. You cannot make this assumption until you write the null. You cannot do a test statistic until you do the assumption. The order that I write this is for a reason. Make sure you follow the order. Now, what did we say? What test statistic are we calculating here? Well, remember, we had n was greater than 30 and sigma was unknown. That is the t-test. So we are going to use t here. Let me scroll down. We're going to do t equals x bar minus mu divided by s divided by the square root of n. Your other choice would have been z, and you would use z if sigma were known. Alright, got to plug stuff in here. Alright, what was my x bar? 172.55 minus the mean. Remember, we assumed the null was true, and the null says 166.3 for the mu. S, 26.33 divided by the square root of n. I can't remember how many men we had. 40. Carefully punch this in your calculator. You might need to take some practice at that. Don't pay attention to what I do because this is a funky calculator. Alright, times 1.501. Alright, so that's my test statistic. At this point, you need to choose which method you're going to use, or read the directions and see which one I tell you you have to use. So we have the p-value method, and we have the critical value method. Alright. Now, in the p-value method, you start with your test statistic, which was 1.501. I like to draw the picture. You don't have to, but I suggest it. It's a good practice. Mark your test statistic. This is a positive one, so it's on the right end. Now, which tail were we testing? Let's go back up. We determined it was a right tail test. So you need to shade to the right. You're looking for this area. In this question, the p-value, because this is a one tail, will equal the area that you find. So, we need to take our test statistic and get an area. That's a t-value. So let's go to our t-table. Get rid of my z. Alright. Degree of freedom was 40. Or, not degree of freedom, the n was 40. So we're going to go to degree of freedom of 30 here. So here, 39. 39, we go across. Where does our test statistic fall in this interval? I forgot, what was it? 1.501. Okay, so 1.501 is actually smaller than all of these in this whole entire line. So it's all the way to the right. So we scroll to the top, we need all the way to the right. For one tail or two. Remember, this is a right tail, so we need all the way to the right of the one-tailed test. So our area is bigger than 0.1. Let's write that down. So our area is bigger than 0.1. Compare that to your alpha. What alpha did they tell us to use here? Alpha, 0.05. So how does this compare to alpha, which is 0.05? Well, your p-value is bigger than alpha because it's bigger than 0.1. What does that mean when your p-value is bigger than alpha? That means you have to fail to reject the null hypothesis. That's the p-value. Now let's do the critical value. Alright, so in the critical value method, you start with alpha, 0.05. You draw your picture, mark your tails. In this case, we only have a right tail, so I'm going to shade that. Remember, all of alpha is in this one tail. So we need to find the t-value corresponding to this area in this one tail. So go back to our t. So, alright. One tail, it was 0.05. So we need to go below this. So this column, go down until we get to our degree of freedom. So keep going. Alright, right here. So I'm below the 0.05 for the one-tailed area. And I've gone across from my degree of freedom. So 1.685. 1.685. And it's right-tailed, so we keep the positive. That's fine. Now what do we do? To finish a critical value method, you compare it to your test statistic. Where does this test statistic fall in my new bell curve? Well, it's actually smaller than my critical value. Remember, if you're in the big section, you failed to reject the null, and that's your conclusion. But remember, you're not done until you've written it in terms of the original claim. So our final conclusion here. There is. Now you could follow the flow chart that I gave you in 8.2. It will still help you here. It's the same flow chart. Same rules apply. Now, because I was in the big section, I remember if I'm in the big section, that means there's not significant evidence. So there is not sufficient evidence. You can also get this from the flow chart. 2. Now, where is my claim at? My claim is my alternative. So there is not sufficient evidence to support the claim. You always want to support the claim if it's the alternative. Okay? So there's not sufficient evidence to support the claim that, and then you write the claim, which I forget what it was. Men have a mean weight greater than 166.33. Is it 33? Nope, just 13 pounds. And you're done. That's hypothesis testing. I've covered all of them. Use the examples in your review sheet. Study all the ones that we've done together in these lectures. And if you have questions, email me and let me know. Good luck.